Hello everyone, this is Unique Bakhrel and I'm here with a video as a part of our project. The project is about groundwater resources in Jefferson County, Texas. Me along with Kushum K C were group members for this project. Let's move into the project. Talking about the project, groundwater resource development is proposed in Jefferson County, Texas by Aquadels Inc. A well is to be installed sufficient for 30,000 municipal consumers. It aims to sell the excess water to industrial and agricultural clients if it is economical and convenient. Consideration for environmental aspect as well as production efficiency is also given. Talking about the objective of our project, there were two parts. It was divided into two parts. The first part was to identify suitable well among three provided locations, for which we need to evaluate wellhead protection areas to each well location, from which we could plot a buffer zone, and using land use, toxic release inventory information, and the buffer zone we created, we had to decide the best well among the three alternatives. In the second part of the project, the capture zone analysis was conducted for the best alternative among the three wells. So talking about wellhead protection areas, according to United States Environmental Protection Agency, a wellhead protection area is defined as the surface and subsurface area surrounding well or well field, supplying a public water system through which contaminants are reasonably likely to move toward and reach such water well or well field. It is a key component of environmental management, especially in regions where groundwater is a significant source of drinking water. Its goal is to ensure that activities in the vicinity of wells do not introduce pollutants or contaminants that could compromise the safety and quality of the water extracted from these wells. The factors that influence the area, shape, and size of the wellhead protection areas are geology of the area, the depth of the well, the aquifer characteristics on which the well is located, and potential source of contamination. Talking about projection, there are three different wells with in three different locations. Well A is located denoted by red star, well B is denoted by purple star, and well C is denoted by green star. All of these three wells were located in Jefferson County. Looking into the parameters, we required 5 parameters to conduct our wellhead to find out our wellhead protection area. The first is time of travel, for which we use 2 years, 5 years, 10 years, and 30 years time of travel. For groundwater pumping rate, we calculated it from the water requirement of a municipality. For transmissivity, we used report 98 and 98B from Texas Water Development Board. For storage coefficient, we used report 320 from Texas Water Development Board. And for drawdown, we calculated it from the natural variation in well water level. Talking about pumping rate of groundwater, as you can see on the screen, we calculated the average per capita daily water used by system size of 2018, from which we found that 137 gallon per capita per day is required as a water demand, and we had to supply the water for 30,000 consumers. So to find out the volume of water to be withdrawn from aquifer, we just multiplied the 137 gallon by number of capita, which was 30,000, to get our volume. This table was extracted from 2020 biennial report, Water Use of Texas Water Utilities, Texas Water Development Board, 7th Texas Legislative Session. After that, we had to find the transmissivity. So transmissivity refers to the ability of water to move through the aquifer. Its unit is a gallon per day per foot. In order to find the transmittivity of our wells, we use report 98 and 98B compilation of results of aquifer tests in Texas, for which transmissivity of different wells in 7 counties of Texas were used. The counties were Orange, Newton, Jasper, Hardin, Liberty, Chambers, and Galveston. First of all, we extracted the data of these wells from report 98 and 98B. We tabulated them in Excel and then saved as CSV file. The CSV file was imported to QGIS, and in QGIS we constructed a Voronoi polygon, and using the Voronoi polygon we found out the transmissivity of these 3 locations. So as you can see in the table, we can find we found the transmissivity of well A as 21,300 and 20,800. It was because there were 2 wells in same location, so we used arithmetic mean of this 2 data as our transmissivity for well A. In case of well B, the well was situated on the polygon with transmissivity data of 30,800, so its transmissivity was 30,800, and in case of well C, the transmissivity was found to be 163,000. All the units were in gallon per day per foot. Talking about the storage coefficient, we used report 320 evaluation of water resources of Orange and Eastern Jefferson counties, Texas. From this report, we found the coefficient of storage ranges from 0.0004 to 0.063, which is also highlighted in the text on screen. The analysis was performed for both the higher limit 0.063 and lower limit 0.004 separately, and the best among these two were chosen as our storage coefficient. And in terms of drawdown, we used water elevation and latitude and longitude of wells data for determining the drawdown. From the water levels measure and well main table, we found the water elevation and longitude and latitude of the wells, and we from the data we found the wells in which measurements were taken for the same well at different times, and using these two data we found the drawdown as the standard deviation of the various measurements from the same locations. After all the 5 parameters were found, we used this solution to determine the radius of the wellhead protection areas. So the equation used can be seen in the screen. Firstly, we had natural drawdown small as the volume of water to be extracted out the discharge. We also have the transmissivity. So using equation 1, we are able to find W. Using the W and using equation 2, we were able to compute U, and using the U, we are able to compute the radius of the wells at different time levels, as small t is the travel of time. So after these computations were done in R programming, and the code for it can be seen in the screen as well. We were able to compute the radius for 3 different wells for 4 different time of travel, and we can see the 2-year time of travel, the radius of the buffer zones ranged from 20 to 50 miles, and for 30 years the radius ranged from 77.5 to 193.5 miles. For better visualization, these were plotted in QGIS. As we can see in the screen, the buffer zone for the wells in Texas for 30 years time of travel reached to the Houston area for all 3 wells, which was quite logical.
Hello everyone, I'm Kushum K C. Now I'll be continuing our presentation from here. So now we have been doing the analysis for the upper limit and lower limit of the storage coefficient, as it has like significant influence on the buffer radius. So for the upper limit of storage coefficient, which is 0.063 according to report 320, the buffer zone analysis for the various time of travel, which is 2 years, 5 years, 10 years, and 30 years, has been done for well A, B, and C. And we can see that for well A, for 2 years, it was calculated using the R code, and it was 1.61 miles. For 30 years, it was 6.22 miles. And this data was plotted using the QGIS to visualize how the buffer zone looks like. The result of which is presented here. So it has the buffer zone for well A. The center circle is well A. This is the clip portion of the Jefferson County. The green ring is the buffer zone for time of travel equals to 2 years. The blue one is for the 5 years. The magenta one is for the 10 years, and the red one is for 30 years. And similarly, we have obtained similar rings for buffer zone for well B, which is a little bit enlarged, and then for well C as well. So after the determination of the buffer zone for 30 years, we use the same 30 years buffer zone for land use analysis, land use land cover analysis. The land use land cover data was downloaded from MRLC website, and it was reclassified as the MRLC reclassification system, and given classified as open water, urban, barren forest, as you can see here. And it was clipped for 30-year time travel. For well A, we can see the maximum area is the cropland and wetlands, and very few urbanized areas, whereas well B has maximum areas covered by the urban areas, which is red here, and it also has the cropland and significant amount of wetland areas. Whereas for well C, we can see maximum is cropland. It has it has the urban areas as well, it has some forest as well. So for determining which well is best for us, only the land cover could not be the best. So we also downloaded the toxic release inventory from EPA website. So it gave the save file for the location of possible source of contamination. We also clipped this data for our 3 wells for the 30-year time period of time travel. So for well A, we had like the minimum number of toxic release inventory TRI, whereas we had the considerably higher number of point source contamination for well B and well C. So considering both the LULC, that is land use land cover, indicating the uh, presence of urban areas, and the toxic release inventory, we came to the conclusion that our well A has the lowest risk of toxic release and also the minimum area of urbanized section, whereas well B has it also extended within the 7 counties, and it has urban area as well, and it has significant number of toxic release inventory, and same goes for well C. And we can see that well C has the larger area covered by 30-year time travel, so it also indicates the higher risk of getting contaminated from enlarged source. So for the part 1 of our analysis, we concluded that well is the most suitable site for us with minimum risk of toxic contamination and lesser urban impacts. So moving on to the next part of our assignment, which was to analyze the capture zone. Let's move forward with the capture. What is the capture zone? So whenever water is flowing in natural gradient in the groundwater, whenever a well is dug or well is installed in any area, it affects a certain area around it through which water is drawn down into the well naturally. So it affects the natural flow of the groundwater system. So capture zone is nothing but a extent of influential area created by a pumping well whenever it is constructed. So for the capture zone analysis, the basic two assumptions that was done was we'll be using it for our well A and considering its center as 0 as the origin, which is 0, and we will first analyze that our flow direction is along the x coordinate, which is the steam. So the equations that will be used for the computation of like the capture zone, which is a curve of the capture zone, that main part is the curve of the capture zone. For the curve of the capture zone, we need to first determine the stagnant point. The stagnant point is a point at the extent from which which is the extent up to which the well can get its water from. So at the stagnant point, we can calculate the axis as stagnant, and at that point y stagnant is 0. So for the calculation of x stagnant, we need to have the pumping rate at which the water will be pumped out of the well, and q naught is the rate of flow of water in the well. So for the rate of flow of water in the well, we have a formula from Darcy's equation, q equals to ki into p, where k into b is the transmissivity, which we already have from part 1, and from there we can get the stagnant point as a stag. And for getting the coordinates of the curve, we need to first find the extent of y, that is the extent of northing up to which the well can influence. So for determining the extent of y, we use the formula y dividend equals to qw by 2 q naught, and then we have the y division. So we have a capture cone curve equation provided to us. So with the help of this equation, we can determine the various values of y's for various values of y's for the various values of determined x in up step. So our first step would be, for the capture analysis, our first step would be determining the natural gradient I. So for determining the hydraulic gradient, what we did was we had the water elevation data from the GWDB website. So we get all the wells in the vicinity of well A, and with the water elevation data and latitude and longitude, what we did is we fitted a linear regression model. Since it's a 3D model, so we fitted z equals to ax plus by plus c in Python, and then we got the values of constants a, b, and c. So as the values are obtained with the linear regression, the hydraulic gradient can be calculated using the formula equals to a square plus b square. So we get the hydraulic gradient of the golf course takeover in the Jefferson County, where our village is located, was 0.001649. And for the real field, we have assumed that the capture zone is parallel to y-axis, but in the real field it's not the case, because water is always flowing through higher gradient to the lower gradient, which is like towards the Gulf Coast in our region. So the plane need to be rotated by some angle. So to determine the angle, we use the formula theta equals tan inverse b by a, and to get the bearing, we added it to 90 degree, and we found out that the plane needs to be rotated by 136.43 degree to determine the actual plane of flow of groundwater. So those values, the coordinates obtained x y division, and the x value corresponding to the y division was plotted in QGIS. This is our well A, which is in the Jefferson County, and this is the curve of the capture zone that we got, so that the water flowing in the natural gradient is on this direction and it is going through this direction, but due to the construction of well here, it captures all the water inner to this curve, and the water flowing on the outer of this curve will flow naturally towards the Gulf of Mexico. So using the reference, these are the reference we used during our whole project, and thank you.